welcome to AKtU University. I am going to discuss the syllabus of electronics engineering. The code is KOE 038 or 48 and this syllabus is running in 3rd semester or 4th semester. Actually this is an elective course and which is launched 2 years ago by AKtU Lucknow. And in the first lecture I will discuss the semiconductor physics. What is semiconductor physics and what is semiconductor, what is doping, why doping is required and how many types of doping techniques are there and how many types of extrinsic semiconductor are there. Okay, guys. So, first of all I am going to discuss the classification of material on the basis of energy band theory. Basically, there are 3 types of materials in our daily life and these materials are divided into 3 types: insulators, semiconductors and conductors. On the basis of energy band diagram, let us say I take an element, suppose I take sodium atomic number 11. The electronic configuration of sodium, that is natrium, is 1s2, 2s2, 2p6 and 3s2, 3s1. The electronic configuration is 1s2, 2s2, 2p6 and 3s1. This means the valence electron is only 1. When we draw the energy level of these valence electrons, suppose there is a small piece of natrium and there are 1 millions of natrium atoms. This means 1 million of valence electrons are there. And when we will draw the levels of energy of valence electrons, then we will get like a band, lines of energy levels, and this lines of energy level is called valence band. Why it is called valence band? Because it is the levels of energy of valence electron, that is why it is called valence band. On the other hand, when we will supply some energy to the valence electron so that it can jump into the excited state, that is it is called the conduction level, and when we will draw the energy levels of all electrons at the conduction level, then we will get lines of energy levels, and this lines of energy level is called conduction band. And there is some energy gap between the conduction band and valence band. This energy gap is called forbidden gap or energy gap. Since I have drawn the energy band diagram of natrium, that is sodium, and this is a metal, so that energy band diagram of natrium is this. Because in case of metal or conductors, the energy gap between valence band and the conduction band is 0, because the valence electron of any metal or conductor, you can say, need not to supply any additional energy to jump into the conduction band. So that the energy gap is here 0. So these elements are known as conductors. This means those materials are known as conductor whose have energy gap 0. On the other hand, if energy gap or you can say band gap is less than 5 electron volt and it is in order of 1 electron volt, you can say, and these are the semiconductors. On the other hand, when energy gap is much higher or you can say greater than 5 electron volt, and these elements are known as insulators. For example, of insulators like wood, plastic, these are the example of insulators. On the other hand, all metals are the example of conductors. Gold, silver, platinum, aluminum, magnesium, natrium, gallium, these are the copper, these are the example of conductors. Among the all conductors, gold, silver and copper are the best conductors. On the other hand, the energy gap lies between the conductor and insulator. These are known as semiconductor, and the energy gap is in order of 1 electron volt. In Moseley's periodic table, especially semiconductors are found in 14th group, that is carbon group. Silicon and germanium are the typical example of pure semiconductors, whose energy gap are in the next slide. You can say here, you can say the energy gap of silicon is 1.1 electron volt and germanium is 0.67 electron volt, and there is a mixed type of semiconductor, that is gallium arsenide, and the energy gap of gallium arsenide is 1.42 electron volt. So, you can say these energy gap are in order of 1 electron volt. This means near 1 electron volt, so that these elements are semiconductor. Now, look at the point that in which form semiconductor are found in nature. For an example, silicon and germanium. We can see that the atomic number of silicon is 14. This means the electronic configuration is 1s2, 2s2, 2p6 and 3s2, 1s2, 2s2, 2p6, 3s2 and 3p2. This means this is the valence electron. Valence electrons are 4 electrons. 4 electrons. Okay, guys. This means the pure semiconductors, that is silicon and germanium, have 4 valence electron, and all of us know that every element wants to fulfill their duet or octet to increase their stability. So, in this order, to increase the stability, silicon form 4 covalent bonds with the 4 neighborhood silicon atom, and it become a silicon crystal. The actual structure of silicon compound is the tetrahedral, but planar structure, the simplified structure is that one silicon atom bonded with 4 sigma bond with 4 neighborhood silicon, and this will continue like this, and this will become a silicon crystal. Okay, guys. But now we want to see that what will be the effect of in this pure semiconductor crystal. What is the effect of temperature? All of us know that with the increasing of temperature, the conductivity of semiconductor increases. On the other hand, with the increasing of temperature, the conductivity of conductors decreases due to increase in the resistivity of the conductors. But there is a opposite phenomena in semiconductor. If we increase the temperature, the resistivity of the semiconductor decreases, that is conductivity increases. Why this is happen in any pure semiconductor? Now, we consider why it is. Because it is the inherent property of any semiconductor crystal that with the effect of temperature, one sigma bond breaks and one electron jump into the conduction band. This is become in the conduction band, and it left an hole. This means when a covalent bond breaks, then one hole and one electrons generates, and this electron hole pair is known as thermally generated electron hole pair. What is this? This is the thermally generated electron hole pair. This means when an electron will liberate from the covalent bond into the conduction band, by default there will be a hole at the valence band. This point to be noted, that holes always are in the valence band. Holes are nothing. This is the deficiency of electron. तो इलेक्ट्रॉन की कमी हमेशा वैलेंस बैंड में होगी. This means holes are always in the valence band and electrons are always in the conduction band. Like every action has a reaction, in the same way when an electron will generate, then simultaneously a hole will also generate at the valence band. This means, what is the difference between the a metal that allows current to flow, this is called conductors. Example, copper, silver, gold, already I discussed. The best conductor have the valence electron, one valence electron, like natrium. Now atomic structure, this is the atomic structure of copper, 29, 2, 8, 18 and 1, one valence electron are at the outermost orbit. This is the atomic structure of copper. Copper is one of the best conductor. This is the silicon. You can say one silicon atom is bounded by the 4 silicon atom, and you can say there are now silicon atom fulfill its octet because there are 8 electrons, and in the same way this silicon will bounded with the 4 silicon atom, and this will also bounded with the 4 silicon atom, and like this. Okay guys, so this is the tetrahedral structure, or you can say compound state of the tetravalent silicon, or you can say germanium. Now this is the planar structure. Planar structure, what will happen when it will gain the heat? The electron will liberate in the conduction band, and here it become a hole. With the increasing of temperature, the number of electron hole pair, thermally generated electron hole pair will increase. This means we can say that the conductivity of the semiconductor also increases. But my point is that at low temperature or at room temperature, the conductivity of the pure semiconductor is like an insulator. So what should we do to boost up, to increase the conductivity of the semiconductor? What should we do? First of all, before discussing the point what should we do to boost up the conductivity of the pure semiconductor, I will discuss how electron and hole, that is thermally generated electrons and holes, are conducting in the pure semiconductor. When we will apply an electric field like this, here positive and here negative, what will happen? The electric lines of forces is like this. This means this electric line of forces, this is equal to E into E, and this means this force will act on an electron in opposite of this direction, and this force will act in the same direction at the hole. This means the movement of electron is from right to the left and movement of holes is from left to the right. Question arises, is holes conduct? Electron conducts or holes conduct? So my answer, and you should know that always electrons conducts, holes never conduct. Holes are seen to be conduct, but the actual movement of electrons are there. Electrons runs or electrons conduct to fulfill the empty place, to fill the empty place. This means the electrons always conduct, but the conduction of electrons happens due to the empty place, due to the holes. This means you should know that the movement of electron will be from right to left if we apply positive here and we will apply negative here, and if the direction of the electric field will change, then the movement of the electron will also change. So, this is the conduction of thermally generated minority carriers. So, already discussed n bond breaks, then n electrons per n holes generate in the pure semiconductor. Okay guys, this means number of free electrons is equal to number of holes. There may be a question will be asked in the examination in 2 marks, that in pure semiconductor, suppose question is this, like this question, number of electrons is equal to erase number of electrons is equal to 10 raised to the power 4, like this, then number of holes is equal to what? It is asked in any pure semiconductor. Then your answer should be 10 raised to the power 4, because in pure semiconductor number of electrons is equal to number of holes, because electron and holes generate simultaneously due to temperature. Now, next point, what should we do to increase the conductivity of the semiconductor? So, before discuss it, we should know that if one athlete goes to any competition like Olympic or any games, so unethically what they did, they take some impurities, some drugs, and when they participate in any competition, there will be a medical test, and if it is become positive, then it is the unethical. This is called doping. This is called doping. In the same way, in the semiconductor physics, if some foreign impurities mixed into the semiconductor crystal, crystal, then it is also called the doping. So, how doping is done? Suppose this is a silicon crystal. Suppose this is the silicon semiconductor crystal, then what will happen? There are 2 types of impurities which has to be mixed into the pure semiconductor. This is from the 14 group, and we have choice here from 13 group and from 15 group. If 13 group is mixed into the pure semiconductor crystal, this means this is the tetravalent, this means 3 valence electron system, and this is if this is the pentavalent, pentavalent, pentavalent means 5 electron system. When this pentavalent 15 group element goes into this crystal, then it will have 5 valence electron and it will have 3 valence electron. When 13 group is mixed, then this will become a p type semiconductor. I will discuss it in the next slide. And when 15 group will mixed into the crystal, it will become n type semiconductor. How it is, I will discuss in the next slide. Here you can see There are two types of impure semiconductor, doped semiconductor. One type is the N type and one type is the P type. N type become due to the doping of the pentavalent and P type due to the doping of the trivalent. And here separately I will discuss this slide. Suppose this is silicon crystal, 4 valence electron, okay guys, and now this is boron. Boron has 3 valence electron. When this boron will doped or you can say diffused into the pure semiconductor crystal, then this will like this, and now boron. When the boron element become in this crystal, then the 4 neighborhood silicon atom will demand the 1 electron to form their valence band, form their sigma bond, but boron have only 3 electrons. This means there will be a deficiency of 1 electron and it is known as hole. It is known as hole. Okay guys, this means if one trivalent atom is doped into this crystal, there is deficiency of 1 electron. If we will dope n number of boron atom into this crystal, there will be a generation of n number of holes, and due to increase this number of holes, the conductivity of this semiconductor will increase. Okay guys, and this hole is always in the valence band, because why? Because the deficiency of electron are always in the valence band. This means holes are always in the valence band. Now question arises that which charge carriers are in majority and which charge carriers are in majority. Suppose guys, we have doped 10,000 boron atoms. How many boron atoms? 10,000. This means holes are 10,000. But at the same time, suppose electron holes pair are 100. This means total holes is equal to 10,100 and electrons is equal to 100. This means holes are known as majority carriers and electrons are known as minority carriers in case of p-type semiconductor. Now, this is the representation of p-type semiconductors. P-type semiconductors, these are the boron atoms, and boron atoms are represented by acceptor ion, because to fulfill their octet, the tendency of boron atom is to always accept an electron. That is why boron's atoms are known as acceptor ion, and with the acceptor ion there are some holes, because the number of holes is equal to the number of acceptor ion. Here, this is the representation of p-type semiconductor. Now, this is the n-type semiconductor. How n-type semiconductor forms? If we doped pentavalent, suppose phosphorus atom, 1s2, 2s2, 2p6, 3s2 and 3p3. This means 5 valence electron system. When 5 valence electron system phosphorus diffused into the pure semiconductor crystal, you can see that phosphorus have 5 electrons. This means phosphorus will share 4 electrons with the 4 neighborhood silicon atoms and fulfill its octet, and after fulfill its octet, 1 extra electrons remains there. This means that 15th electron is extra for phosphorus. This means that phosphorus atom can easily donate the 15th electron, or you can say 5th valence electron. After donating this 5th electron or 15th electron or 5th valence electron, it will become positive ion. That is why phosphorus pentavalent atom is known as donor ion. And here electrons are majority carriers and holes are in minority carriers. Okay guys, why electrons are in majority carrier? Suppose we have doped 10,000 phosphorus. This means there are 10,000 free electrons, and at the same time there are 100 electron holes pair which are thermally generated. This means total electrons equal to 10,000 plus 100. This means 10,100 are electrons and 100s are holes. This means electrons are in majority carriers and holes are in minority carriers. And this is the representation of p-type semiconductor. The plus nucleus circled plus, these are known as donor ion, and one donor ion has one free electrons. This is the representation of n-type semiconductor, and there are some minority carriers also which are known as electrons. So, overall the conclusion is that we have doped to increase the conductivity of the pure semiconductor, and after doping now the semiconductor is known as extrinsic semiconductor, and there are two types of extrinsic semiconductor, p-type and n-type. In case of p-type, holes are in majority and electrons are in minority, and in case of n-type, electrons are majority and holes are in minority carriers. So, thank you guys, we will meet in the same next lecture very soon.